Let's talk about vectors in 2 dimensions. We know that a vector in 2 dimensions can be defined by its horizontal component and its vertical component, or it can be defined by its magnitude and direction. And we want to be able to go back and forth between those depending on what we're doing with the problem. Before we get to this problem, I want to define a direction angle. The direction angle of a vector is the positive angle between the x-axis and a position vector. So let's move down to this problem and see this at work. It says we're to find the magnitude and direction of the vector v, and notice I gave it in component form. So we can just draw a picture, as we so often do in trig. So let's draw a picture of v, and we'll put its initial point at the origin, and its x component is 7 and its y component is -7, so it's going in this direction. So I know this is 7 and this is -7, and this is a picture of vector v. Well, in order to find its magnitude, we just need this side here, the length of this side. We know the magnitude of that vector is just the square root of 7 squared plus -7 squared. That's the square root of 49 plus 49 is 98, which is 7 square root of 2. But I hope you recognize that we didn't actually have to go through that work. Did you see that we were really talking about our special triangle, our isosceles right triangle, and we know if this is of length 7 and this is of length 7, this is 7 square root of 2. So you don't actually have to go through that process. Similarly, for the angle, and we're trying to find this angle right here, I don't even need to set up an equation with a tangent like I could, because we recognize this as a 45-degree angle. So if this angle right here is 45 degrees, we know that theta is equal to 360 degrees minus that 45 degrees. So our direction angle for this particular problem is 315 degrees. And the problem is done. Let's do another problem, similar. And this time I've just used our other notation. I used our unit vectors when representing the components of our vector v. But the idea is still the same. We're to find the magnitude and direction of the angle. And as I did on the previous one, I'm going to draw a picture of it. So our vector v is going -4 in the horizontal direction and +9 in the vertical direction. So our vector v looks something like this. Need a direction for it. So the 2 questions are find the magnitude. So this is not one of our special triangles this time. Let me label this. This is -4 and this is 9. So to find the magnitude of v, and notice I accidentally actually, in this previous problem, I used just 1 set of vertical bars, and here I did 2. Both are so common. I'll try to be consistent and put 2 in each time, but you see it both ways. So if I inadvertently show it one way versus the other, don't let that throw you. So the magnitude we know is the square root of -4 squared plus 9 squared. Means we have the square root of 16 plus 81, or the square root of 97. So now we know the magnitude of this vector is the square root of 97, something a tad bit smaller than 10. Now to find theta, notice theta's right here. We have our reference triangle. We know the tangent of theta is going to equal our y value of our x value, so -9/4. So if we take the inverse tangent of theta, inverse. I didn't write the inverse sign. Inverse tangent of theta. It won't quite give us what we need because remember the inverse tangent always gives you an angle between negative pi over 2 and pi over 2. So if you take the inverse tangent of a negative ratio, it's going to give you the angle down here. So 180 degrees away from this terminal side up here. So we're just going to add that 180 degrees to it. So our inverse tangent gives us this angle down here, but we want this angle. So if we take the inverse tangent, make sure you're in degree mode since we're working in degrees now. Inverse tangent of -9/4 and add 180 degrees to the nearest tenth of a degree. Let's see, what do we have? 113.96. That is 114.0 degrees, just depending on how many decimal places you need. Maybe we would present it as just 114 degrees. But to the nearest tenth, it is 114 degrees, which seems about right given our picture. I like to make sure that my answer seems to match what my picture looked like. Let's keep going. Suppose that instead of knowing the x and y components, suppose that the magnitude and the direction are known. If the magnitude and direction of a vector are known, can you find the vector in component form? Well, let's draw a picture of a vector where we know its magnitude and direction. So let me make this vector v. I'll just put this as our vector v. We'll just say that's our vector v. But we know its length right here is the magnitude of v. So let me label that as the magnitude. I'm just writing that as its length. The entire vector itself, both with its angle and magnitude, is the vector, but its length is this. Now the angle, we'll just say, is known to be theta. The question is, can we come up with the components? Can you come up with this x value and this y value? And I hope you recognize that we have seen this in trig many times, pictures that look like this. Our job is to find x and y. So cosine of theta would equal x over the magnitude of v. And similarly, the sine of theta equals y times over the magnitude of v, right? Our x over r, our magnitude of v is playing the role of r. And when we multiply by the magnitude of v, what we see is that the x component of the vector is the magnitude of v times the cosine of the angle. And the y component of the vector is the magnitude of v times the sine of the angle. And we can use that when we're trying to find the components of a vector. So let's do this particular problem. So this says to find the component form of a vector v, given that its magnitude is 10 and its direction angle is 210 degrees. If I just stuck strictly to this formula, the x component and the y component, notice we could find that vector v this way, that we have the magnitude of v times the cosine of theta will give us the x component, and the magnitude of v times the sine of theta will give us the y component. Now let's substitute those values in. So we have 10 cosine of 210 degrees, comma, 10 sine of 210 degrees. Let's substitute in the values that we know. Let's see, 210 degrees is in the third quadrant, so the cosine is negative. Our reference angle is 30 degrees, so we know that it's going to be 10 times negative square root of 3 over 2. And The y component, we have 10 times the sine of 210 degrees. Again, a third quadrant angle, and the sine is negative in the third quadrant. Reference angle is 30 degrees, so we have negative 1/2. So the component form of the vector described is negative 5 square root of 3, negative 5. And I hope you would recognize if we draw a picture, this is exactly what we would expect. Let's draw it. This component was negative 5 square root of 3. The y component is negative 5. And we have our special triangle, our 30-60 right triangle, with this being our 210 degree angle. So this is 30 degrees, and this is 60 degrees, and notice the ratio. We have a negative 5 and negative 5 squared of 3, and we know that would mean this is 10, as expected. So the picture confirms what we already knew. Let's do another one. Right here, find the component form of a vector v, given its magnitude and direction. And again, we could go right to the formula, or you can draw a picture. I'm a fan of drawing the picture. It just makes me feel better. I can confirm I seem to be on the right track. So 112 degrees we know is just a little bit beyond 90 degrees, but we have a second quadrant angle, so we have theta here, and we know the magnitude of this vector is 95. And so we're being asked for this x value and this y value essentially for the vector. So here we go. The vector v is equal to the magnitude times the cosine of the angle, comma, the magnitude times the sine of the angle. Now these aren't any of our special angles, so we grab our calculators and we punch those in. We have 95 times the cosine of 112 degrees, and to the nearest tenth you get negative 35.6, and we have 95 times the sine of 112 degrees, and you get 88.1 to the nearest tenth. So this is actually approximately equal to right here, and not exactly equal. And I peek back at my picture, and it seems about right to me. This is, if this is length is positive 95, then this length is negative 35.6, and this is 88.1. And so it seems about right. So I have some confidence that my answer is correct. Let's do another problem. Suppose a bullet is shot with an initial speed of 720 meters per second at an angle of 40 degrees from the horizontal. Find the vertical and horizontal components of the velocity. And I just want to mention that sometimes people use velocity and speed interchangeably, but in fact, they aren't the same. The speed is actually the magnitude of the velocity. The velocity represents both the speed and the direction. You need both for the velocity. So the vector that represents the velocity, let's draw it. Let's see, 40 degrees right here. This represents the velocity, so its magnitude is 720. So that's our speed, but also important is that we have a 40-degree angle. So let me just mention, if you change the angle of the shot, even though it would still be going 720 meters per second, its velocity will have changed because the angle is a part of velocity. But let's now find those components. We know, I'm just going to call this the vector v, and it's equal to, just as we did before, 720 times the cosine of 40 degrees, comma, 720 times the sine of 40 degrees. And if we punch those in on our calculators, we get 720 times the cosine of 40 degrees. We get about 552. I'm going to the nearest whole number. And similarly, if you punch in 720 times the sine of 40 degrees, you get about 463. So the horizontal component, so we're talking about this horizontally, is 552 meters per second. So the horizontal component of the velocity is about 552 meters per second, and the vertical component, going in this direction, is 463. So the vertical component of the velocity is approximately 463 meters per second. And let's do one final problem, sort of the grand finale for this work on vectors. Here is the problem. It says 3 forces with magnitudes of 200 pounds, 95 pounds, and 130 pounds act on an object at angles of 50 degrees, 170 degrees, and negative 40 degrees, respectively, with respect to the positive x-axis. Find the direction and magnitude of the resultant of these forces. So I've drawn the picture of these forces. So here's my picture so that we can talk about it. The first one, notice, was 200 pounds at an angle of 50 degrees. So here we are, 200 pounds at an angle of 50 degrees. Notice it was our largest force, so I represented it with the largest vector, or its magnitude was the greatest. The next one, we have a force of 95 pounds and an angle of 170 degrees. So here it is, 95 pounds. I made it just a tad bit shorter than half of this. I hope it probably looks like about half, because its magnitude is half, and an angle of 170 degrees. And finally, the third force was 130 pounds and an angle of negative 40 degrees. So consider these 3 forces acting on an object. So what's the result? Can you envision what would happen? We have one large force this direction, another relatively large force this direction, but it's being held back or pulled this way by another force acting in this direction. What would be the result? Do you see that the result will be as if the more force is going to the right instead of to the left, but this force will be pulling it back a little bit? Let's add the vectors. Remember, the resultant is what you get when you add the vectors. So I drew the picture of each of these vectors. So here was the vector u. I drew it right here. Now, the resultant vector is the sum of the 3 vectors. So our goal is going to be to find this vector. And by the way, you may or may not have noticed that when I added them, remember, it's initial point to terminal point, initial point to terminal point, initial point to terminal point. I just like the picture better when I commuted the v and the w, but remember, vector addition is commutative, so I just preferred to add u plus w plus v. So I can even write that, u plus w plus v, because we know we can add them in any order. But the result, here is our resultant vector. That result will be comparable to a single force adding in this direction, or acting in this direction. So our job is to find the direction and magnitude of this vector right here. So let's start by finding u, v, and w in their component forms. So let's come back here. I think we'll work with this particular picture. And we're going to find u, v, and w in component form. So let's start with u. U equals magnitude 200 times the cosine of the angle, comma, 200 times the sine of the angle. Oop, it's a vector. I meant to use that chevron, not parentheses. If you punch that in on your calculator, you'll get approximately 128.6, 153.2. So that's this u vector. Let's move on. Vector v. Now its components, well, let's see, its magnitude is 95. So we have 95 cosine of 170 degrees, comma, 95 sine 170 degrees. And if we punch those in on our calculator, we'll find that the components are approximately negative 93.6, 16.5. And notice that seems about right given the picture here. Negative x component, small positive y component. And now I'm on vector w, which is 130 times the cosine of negative 40 degrees, comma, 130 sine negative 40 degrees. So it would be approximately equal to, we'll punch this in on our calculator, and we get 99.6 and negative 83.6. And again, I peek back at my picture to see that it seems about right. If this is 130, 99.6, negative 83.6 seems about right to me. So the resultant vector, let's find it right here, which we know is u plus v plus w, means we will add all of the x components. So we're adding 128.6 plus negative 93.6 plus 99.6. And if you do that addition, you'll find that you get 134.6. Similarly, we're adding the y components, 153.2, 16.5, negative 83.6, and if you add those together, you get 86.1. So here is our resultant vector in component form. Let me bring back the pictures. Let's see if it seems about right. Here's my picture. I didn't actually label any scale, but notice first quadrant, positive 134, positive 86.1. Seems about right. Let's put this on this page. 134.6, 86.1. So we have our component form of the resultant vector. But let's see, what was the question? The question was to find the direction and magnitude of the resultant. So we have the vector now in component form. All we need to do is find its direction and magnitude. So here we go. Let's find the direction. That means we're finding theta right here. And now what we know is these values are, I can even draw it in. I know this is 134.6 and this is 86.1. So we know the tangent of theta. Let's put it right here. Tangent of theta equals 86.1 divided by 134.6. That's here in the first quadrant. So if we do the inverse tangent, it will give us an angle. Let's punch that in. So we have inverse tangent of 86.1 divided by 134.6. And we get about 32.6 degrees. And now we want its magnitude. So we're finding the magnitude of U plus V plus W. Magnitude. Well, we have these two components. We know it's the square root of 134.6 squared plus 86.1 squared. And we just have a problem to punch in on our calculator. If you do that, you'll find it's approximately 159.7, and we could say 160. So 160 pounds. So those three forces, remember here was the picture, or there was the problem, and here was the picture. If we have these three forces acting on an object, it would be comparable to a single force that has an angle of 32.6 degrees and has a magnitude of 160 degrees.